Mr. Otto Vangeet is a principal engineer at the NREL laboratory. Otto has been involved in the design, construction, and operation of energy-efficient research facilities, such as laboratories and data centers, office and general use facilities, and low energy use campus and community design. Mr. Vangeet was one of the founding members of the Lab 21 Smart Labs program and provides technical guidance for the program. His experience also includes renewable energy screening and assessment. Please welcome with me Mr. Otto Vangeet.
Good morning, everyone. Again, I'm Otto Vangeet from the National Renewable Energy Lab, or NREL, in the state of Colorado in the United States. And wanted to talk to you today about energy efficient laboratory, safe laboratory buildings. And the title of the talk is Work Smarter, Not Harder, Improving Energy Efficiency and Safety Through Smarter Ventilation. And I wish I could be with you there in person to present this, but we'll make this work. So thank you for this opportunity. And I wanted to do a quick set of acknowledgments from the U.S. Department of Energy. Jeff Morrell sponsors this work. I'll talk about the Smart Labs program and partners. We had a couple dozen partners, and I'll talk about some of those. Also the International Institute for Sustainable Laboratories, I2SL. And we just had our annual conference this week. It just concluded yesterday in the city of Pittsburgh in the United States. And then Tom Smith from the company 3Flow. So getting on to why labs. Labs use 3 to 5 times more energy than an average office building. But because of that, there's also huge opportunities for large cost savings, often 20, 40, maybe even 50% cost savings based on opportunities and lab spaces found in the case studies. And I'll elaborate on those in this talk. And with large cost savings, $1 to $2 billion in US, obviously much more if you can include all the laboratories in the world. So energy use in laboratories. Laboratories use 100% outdoor air for ventilation for safety reasons, which will be the focus of this talk. And that energy use for that ventilation is by far dominates the energy use. And it's for moving the air and then conditioning the air, heating it, cooling it. And that's often 3/4 of the energy use and by far the largest opportunity. But there's other opportunities for things like plug loads from research equipment and normal things like lighting, which I won't spend much time on because it's very similar to other buildings. So the solution that we and again I2SL have come up with is Smart Labs. And it's a Smart Lab program that goes through different phases, different steps, a planning step, an assess step, an optimize step, and then a manage step. And I'll end up talking about all those more during the talk. But the intent of this program is to create world-class science through the design and operation of safe, always safe first, and efficient high-performance labs, with the result of optimized safety, improved energy efficiency, reduced cost, and maintenance of high-performance laboratories through the life of the labs. So some of the key elements of the Smart Labs, and I'll go through this in the next few slides, is it all starts with a ventilation risk assessment. And I'll talk a lot more about that, but that's basically what are the hazards in the air based on the use of chemicals. And from that, we can optimize the airflow. And in doing that, what we want to do is select and place diffusers in the right location, typically near the entrance of the lab. So like this image is showing, So you can kind of sweep the air across from the entrance, the cleanest part, away from the researchers and out to either the general exhaust in this image, or on the left-hand side of the image into an exposure control device, such as a fume hood. To be able to get this all to work optimally, you need variable air volume controls for the laboratory space, meaning controlling the airflow in the exhaust and correspondingly to the supply. And that those same controls would typically keep the lab space at a negative pressure. So if there's any leakage, it's leakage into the lab, not out of the lab. We also want to use minimize fan energy by selecting efficient fans, of course, and then low pressure drop design, so large, smooth ductwork. And then we need to discharge the potentially hazardous air in a safe location. So using tools such as wind tunnel modeling for figuring out the height and the location of stacks and the appropriate discharge velocity. And it turns out from that modeling, you can also determine what the safe velocity is, and it varies by wind direction. Kind of makes sense, but often you can ramp down the velocity when there's less wind or when wind is from a favorable direction. That can lead to other large savings. So the other part we want to do, and it relates to what I just talked about, is obviously high ventilation effectiveness. So you're getting a very effective flush of the air through the space. And then we, of course, want to do other things like occupancy-based ventilation controls. So if there's no people in the space, you can probably use less ventilation air because there's no people to get exposed, of course. And using those same sensors to control the LED lighting, similar to an office space, actually even more important in the lab because there's typically slightly higher lighting power densities because of the work in a lab. It also makes sense to optimize your research equipment. Things like ultra low freezers, if you have those, can vary dramatically in their energy use by the model you choose, similar for autoclaves and all types of research equipment. And perhaps most important, the spaces for the researchers for doing world-class research, and having informed researchers is probably the most important. There's programs such as for My Green Labs that work on getting informed researchers, but it's simple things like closing the sash on a chemical fume hood to make them safer, most importantly, but also to reduce the flow rate when the sash is closed. It goes down correspondingly to the opening of the fume hood. So how can smart labs help? So again, we developed this toolkit. An image of it is on the right-hand side. It's smartlabs.i2sl.org, and you'll see that a few times, or you can just search for Smart Labs Toolkit. And it walks through all the things I'll talk about here, again, through a plan, assess, optimize, manage process. And at the center of that is a Smart Labs team with the Smart Labs coordinator, informed researchers, management and facilities, and environmental safety and health professionals. And what the toolkit does is provide partner case studies. I'll show you one of those later. Step-by-step guidance, user-friendly tools and calculators. I'll show you some screenshots from some of those, and all kinds of resources and templates and best practice guides, for what's the best way to do variable air volume or manifolded exhaust or dozens of other things like that for laboratory buildings. So the Smart Labs process starts in the plan in the bottom left-hand portion of this slide, where you build a team of lab stakeholders, profile buildings to prioritize your efforts. Start with an easier building to get this process down, and then work towards your more difficult buildings. And then from that, develop a strategic plan for cost-effective implementation of the things you find from the assess phase. And in the assess phase, you conduct in-depth audits of the laboratory buildings, focusing on the ventilation systems. From that, you develop a scope of work for system optimization. And you do that now in the optimize phase. So this is a circular plan, and then assess, optimize, manage. Optimize, you actually execute the meaningful projects with demonstratable payback. And then you develop a building management plan to outline dynamic management for optimizing operations. And then once you've done optimizing that and commissioning it and verifying it's working as intended, then you go into the management phase where you implement lifecycle performance management and apply lessons learned in improving additional facilities in the campus. And you stay in that phase until there's some change, a change in the research or a new set of equipment or new chemical usage, et cetera. Then you probably have to go back and do an assess and optimize again. And what it might mean is you might change the ventilation rate, or you might add or remove exposure control devices, all those sorts of things. So really the heart of this is, again, the ventilation risk assessment and using the laboratory ventilation, using the LVRA tool. And what this tool does is you're using conducting surveys, first of your exposure control devices. Again, think of fume hoods, but it can include biological safety cabinets or however you're controlling that hazard. And what we're doing is evaluating the characteristics of the hazard and the risks, and assigning a risk control band to it ultimately, from 0 for negligible risk to 4 for an extreme risk. And you do that for all exposure control devices. Then you do the same kind of thing for the actual lab space. And you, again, go through 0 to 4 and include the risk control bands from the exposure control device survey. Overall, then, you can get a hazard for your exposure control device and your lab. And then what we do is use that hazard rating, that risk control band, to determine the appropriate ventilation requirements. And ASHRAE has luckily come up with very good guidance on this for both the exposure control devices and the room from the ASHRAE laboratory design ventilation rate recommendations. And then you can compare minimum and maximum flow rates for your room and your device, again, using those guides. Just a quick LVRA tool demonstration. You go through, and again, starting in the left, you enter different data fields, and there's pull down menus. You can see it being simulated here. And based on the hazards and the quantities and such, enter numbers, you'll come up with a risk control band for the exposure control device. In this image, it was 4, so a high hazard. And then you'll do the same thing for the laboratory space. And again, putting in numbers, you can see we're virtually entering those here. And then it'll go through, determine the recommended air change rates for the lab. In this case, it was 6 and 4. And then you'll implement that in the space. And I encourage you to, it's all free. It's an Excel-based tool. And it's based on industry best practices for characterizing and controlling the ventilation rates in lab spaces. The Smart Labs tool also has several other sections. I'm not actually going to demonstrate those, but I encourage you to go there. And it's a lot more detail on, again, all these phases: the plan, the assess, including the tools, the optimize, the manage, and then there's also sections on working with scientists, decarbonization of laboratories, and then many resources. So I encourage you to take a look at that. Again, smartlabs.i2sl.org. You can see it in the screenshot there. And with that, I'll kind of give you one example. We worked again with a lot of partners in the United States, but we've actually this program we've done it in other countries also. And I would encourage there's chapters of I2SL around the world. But anyway, the example here is from the University of Minnesota in the United States. And what they did is they worked with their environmental safety and health staff and developed a performance-based alternative design process. From that process, they determined the risk control bands, again, using the tool that I talked about, and the appropriate ventilation safety design. They documented that and the activities and documented the chemical inventory and use that all to determine the flow rate in the assess phase. Some clever things they did in the optimize phase is used kind of a hoteling, if you want to use that term, concept to group similar work activities. So keep the low hazard activities in low hazard spaces, and you can run that at a much lower air change rate, and correspondingly high hazard and high hazard spaces where there's probably also more fume hoods and correspondingly high ventilation rates. And also moving chemicals instead of keeping them on the bench to keep them stored in ventilation storage cabinets. And then during the assess and optimize phase, they created a safety plan toolkit to document the safety procedures. And they do inspect the labs every 6 months to make sure they're still operating as intended and that the key performance metrics, such as air change rates, are being met. So with that, I am done. I would again encourage you to go to the Smart Labs Toolkit, and there's many more things on there. And with that, I'll take some questions if you have them. Thank you for joining me today.
Thank you for your presentation. We have time for a couple of questions. So if you want, I have a small question or a comment that concerning your lab. Do you have international cooperation or exchange with other institutions? For example, Lebanon can be.
So could you repeat the question? I'm sorry.
Actually, you were talking about the lab, the smart labs. So my question is for your if you have an international exposure and if you have cooperation or you are collaborating with other institutions on these labs.
Yeah. Thank you for clarifying that. We do work. Again, I2SL is a worldwide professional organization, very similar to ASHRAE. Works with ASHRAE. They do have chapters around the world, and again, go to i2sl.org. For example, there's a Singapore chapter and there's a China chapter. I do not know of a Middle East chapter, and there's UK and other EU countries. I would encourage potentially forming a Middle East chapter, such as in Lebanon, and we would be interested in talking to laboratories at a university, for example, in Lebanon. But we currently do not, that I know of. But again, if there's questions, we'd be very glad to help. That's half the reason for this presentation. Either through I2SL or just contact me at this email, or through ASHRAE, whatever's most appropriate. Does that answer that question?
Yes. Thank you.
Excellent. Yeah, and for everybody listening in, please feel free to email me at this address.
Thank you for your answer and also for your presentation. If we don't have any more questions, we can end the session. And I would also I'll be very happy to thank you for this day, and we welcome you for tomorrow, the second day of the conference. So see you tomorrow, everyone, and have a nice evening.
All right. Thank you, everyone. Have a great conference.